looks like it's going to record. If anybody notices this say that it stopped because the memory was full or something, let me know, because it did that during second period halfway through, and I just said I'll record third. But if it does it again, I won't have another class to do that for. So regular right triangle trig is sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. This is like the first thing you learn about trig, and these ratios only apply for right triangles. Whenever you're looking at applying this, you may have learned, like, to help you remember these ratios, you may have learned like SOHCAHTOA, possibly, or I teach my class whenever I used to teach this. I teach some old hippie called a high tripping on acid. That gives you SOHCAHTOA. One time I mentioned something about this to my husband, and he said, "Oh, that's Oscar has a hairy old arm," we'll say there, or replace arm with other body part that starts with A of your choice there. I don't even know where he learned that, because we had the same geometry teacher when we were in high school, and she definitely did not say that. But Oscar has a hairy old arm right there. So those are really important for you to have memorized for just being able to use regular trig in any circumstance that you might find it. So if we look at a couple questions where we're going to do this, if we look at example 1, it tells us to find the length of DE. So DE is this side right here, and let me get a pen right here. So like I'm going to put an X right here. That's what we're looking for. So whenever we're doing trig, you have to have a right angle, but the right angle is not the angle that you use for the trig. You need to use this angle 42 degrees. And so these sides, the side across from your right angle is always your hypotenuse. That hypotenuse is your longest side, and it's always across from the right angle. And then across from this 42, we call that the opposite side. And then we would call this 12 right here my adjacent side. So in this case, I do not know or care anything about the opposite side, right? Because I don't know it and I don't need to find it. So I'm not going to use it. I want to use adjacent and hypotenuse. So which trig ratio should I use? That one's going to be cosine. So we will set it up cosine. That theta right there is an angle. In this case, it's 42 degrees. Equals our adjacent side, which is 12, over our hypotenuse, which is x. And so when we're solving this, you cannot solve for something when it is in the denominator of a fraction. So that x right there is in the denominator. I'm going to multiply by x to cancel it out. I'm going to multiply by x over here. So I will get x cosine of 42 equals 12. And cosine 42 is a number. In fact, lots of you probably know Jane Hendrick, that used to work at the middle school, and she tutors a lot. Miss Hendrick talked about whenever she was in high school having a table of trig values that she had to use because she did not get to use a calculator that had sine, cosine, and tangent. Like, they didn't have them. Which, I mean, she's retired. It's not like she's super young, but I mean, she's still very much alive and kicking, and had to have that table to use. So we thankfully have a calculator that stores all those values for us, so we don't have to reference the table. But this is a number right here, so we're just going to divide it off. Here, so x is going to equal 12 divided by cosine 42. Now you won't have to do this much because our entire exam is going to be in radians instead of degrees. But right now we had cosine of 42 degrees, right? So whenever I type this in, if I do 12 over cosine of 42, right here, I'm getting negative 30, which is not right because, like, I would not even call something a negative angle whenever I'm talking about just a regular old triangle. That is because your default on Desmos is radians, so I need to click it over here to degrees. That's not going to become an issue much because we're going to use radians instead, but right now we're just doing a little bit of review. So I get 16.148 for that. So x is 16.148, whatever the units are for this here. And that looks about right because it is definitely going to be longer than 12 for that. Okay, questions there? It's familiar. You remember maybe back to Math 2. Maybe you've at least seen it before, hopefully. Let's look at number 2 because it's a different type of problem. So number 2 asks us to find the measure of angle T. So in this case, we're looking for this angle right here. I'm going to call it theta because a lot of times we like to use the Greek letter theta if we have an angle. You don't have to. You could call it x if you wanted to here. And for that angle right there, 7 is my opposite, 24 is my adjacent, and 25 is my hypotenuse. So in this particular case, I have all three sides. So does it matter whether I use sine, cosine, or tangent? It does not. So Hayden, what is your favorite sine function? Which one do you just like the best? Or I said fine. Yeah, sine's your favorite. I kind of led you to that because I said sine function. But sine is our favorite here. So we're going to say sine of theta equals, the opposite would be 7. Hypotenuse would be 25. But we don't have to use sine. You could use cosine or tangent on this one because you know all the sides. So who can remember how I solved this? Oh gosh, James, you remember too much. They struggled with that in second period. Inverse of trig functions. I was going to let at least one person tell me I needed to divide by sine. Somebody was probably thinking about dividing by sine, maybe, except for James said it so quick that you didn't even know. But yes, very good. So in this case, like my second period told me I needed to divide by sine right there. But if you try to divide by sine, if you had 7 over 25 and you try to divide by sine, nothing's going to happen because you have to be doing sine of something, right? So we can't divide by sine because it's not a number, right? It's not even a variable. It is an operation. So in order to undo sine, you have to use inverse sine. Right, so just like addition and subtraction are inverses, multiplication and division are inverses, logs and exponentials are inverses of each other, sine and inverse sine are inverses. So you're doing inverse sine of this sine over here, which will cancel that out. You'll just have theta. And then you'll do inverse sine over here. So we got theta equals sine inverse of 7 over 25. Which we are going to type into the calculator. And I don't think it works to do sine like to the -1 power, because I tried that in second period and it was not working. So you actually have to go to functions and use sine inverse, and we're going to do 7 over 25 right there. Okay, check it. It wasn't working for me in second period, but maybe I was doing something wrong. All right, we got 16.260. Now, we are still in degree mode. So if I'm in degree mode, this is a degree answer. This particular problem did not tell me.
It works just fine.
It does. Maybe I didn't type it in right. Oh, it was just me. I probably didn't have parentheses yet, maybe. I gave up probably too quick. I think what I did is I did sine to the -1. I probably just needed some parentheses. I don't know if I got to actually plug in the number. was doing. Failing, obviously, is what I was doing. So, for this, I've got inverse sine right here. I'm in degree mode, so it's giving me a degree answer. This particular problem did not tell me whether to use radians or degrees. So, if you needed radians, we could flip this back to radian mode, and notice it changes the answer. We could do, theta could also be 0.28, what was that? 284 radians. If you want to switch back and forth, the little wrench button up here in the corner, down here at the bottom of that box, it says radians and degrees. In general, we're just using degrees a little bit right now because it's more familiar to us. But in general, everything on my test and on the exam is going to be in radians, and radians is the default, so you shouldn't have to switch back and forth for it. There. Okay. Questions? Okay. So this next slide is on special right triangles. I know Miss Martin does this. How many of you had Mr. Brown for Honors 2? Several of you. Do you guys remember if you saw special, like 45, 45, 90 triangles and 30, 60, 90 triangles? Yeah, there's no telling. There's a decent chance that he did not do that, which is like acceptable for Math 2 because it's really just a shortcut and you could use regular trig for it. So I have had classes before where I did not teach it to them because we were running short on time and they were already like struggling, so we didn't add one more thing in there. But this is just a shortcut that is always going to be true. I realize you took the ACT Wednesday, so now is not the best time for me to be telling you this. And you might not have even seen any questions like this, but you could have. This is helpful. If you see a 45, 45, 90 or 30, 60, 90 triangle on the ACT, it is helpful because it speeds you up a lot. So it's going to help us whenever we're filling in the unit circle, because if you're remembering anything about the unit circle, you should remember there was a 30 degrees and a 45 degrees and a 60 degrees that were pretty important points on that graph. So, for a 45, 45, 90 triangle, these two angles right here are congruent to each other. So whenever you have an isosceles triangle where you have those two angles the same, the sides across from them are the same as well. So both of these are marked as X because those two sides are going to be the same. So whatever this side is, if you want to know the hypotenuse, you multiply by the square root of 2. So if this side is 7, then the hypotenuse is 7 times the square root of 2. Or if this side is 12, this side is 12 times the square root of 2. All right, so it just always works like that. So if you were to see a problem, like on the ACT or something, and they just gave you something like this, 45 degrees, right triangle, 5 right here, you would say this is 5 square root of 2, and you would be able to answer it in seconds and move on, right? So I don't know if you ran into one of those or not, but it could have been helpful there. 30, 60, 90 triangles have a slightly more complicated rule, but still much quicker than working out the regular trig for it. The side you really want to know in a 30, 60, 90 triangle is the short leg. So those two sides that are perpendicular to each other, the sides that are not the hypotenuse, are called the legs of the triangle. And the shorter one is always going to be across from that 30-degree angle. The longer one will always be across from the 60-degree angle. And if you know this short leg, then all you have to do to find the hypotenuse is multiply that by 2, right? So, like if this side is 3, the hypotenuse is 6. 2 times 3, which will give you 6. To find the longer leg, you take the short leg and you multiply by the square root of 3 for that. And so that is just always true for these triangles. You can do regular trig. It gives you the same answer. The thing is if you do this on the calculator and get the same answer, it's going to give you the decimal version of it. And on the unit circle, you can probably remember enough to know there were no decimals that you were memorizing for that, right? It was all fractions that you were looking at. So this also is helpful in that way. So let's just do a couple examples. If I have this 45, 45, 90 triangle right here, and I want to find the length of this leg right here, what should I do? You could do that, yep. We could say 5 is the square root of 2 times x. So then what would we need to do right here? Divide by that square root of 2. So x is going to equal, oh, sorry, that didn't have square root, 5 divided by square root of 2. We are going to need to rationalize denominators, but I got another slide on that, so I'm going to just leave it for right now. Yes, we'll rationalize denominators, but I got another slide on that, so we'll worry about that when we get there. So that would be your answer. And you can really just think, like, to go from the leg to the hypotenuse, you multiply by the square root of 2. So to go from the hypotenuse to the leg, you divide by square root of 2, right, for that. Now, what about number 4? I've got in this case, I've got the short leg, which is good. That's the one that you want to know, the short leg. So what do I need to do to find the hypotenuse on this triangle? Multiply it by 2. So I'm going to get, in this case, x equals 2 times 3 square root of 3. And to multiply radicals together like that, you just multiply the numbers on the outside together and the numbers on the inside together. Obviously, we only have outside here, so we get 6 square root of 3 for that one. So these are good shortcuts to use. They're going to help us with the unit circle a little bit because these angles show up in the unit circle. For that, let's keep going. One more thing we need to make sure we know how to do is we need to know how to rationalize the denominator of a fraction. So in general, mathematicians have decided it is a bad idea to leave a square root in the denominator of a fraction. I don't even buy that it's all that important, but because either way, like square root of 2 is an irrational number, which means it is a decimal that goes on and on and on and on and on forever. So textbooks at least have decided that we should not be dividing by an irrational number. Now, this is still an irrational number even once we rationalize the denominator. So like you're going to have the irrational number is going to be in the numerator instead of the denominator whenever you work with these problems. So, you know, in our class, we have to rationalize denominators. The directions on our FRQ questions tell us we have to rationalize denominators. When you actually get to calculus, you don't have to rationalize denominators on the FRQs. You could just leave your answer as 5 over square root of 2. Now, on a multiple choice question, they're still going to rationalize the denominator because it's the standard way to leave the answer there. But, so you may or may not feel that this is very important, but we have to do it either way. Because typically, whenever I do this right here, especially example 5, the answer to me looks more complicated than what we've got to begin with. So I need to get rid of the square root in the bottom of that fraction. Any ideas on how I can do that? Yes, I can multiply by the square root of 2 as long as I also multiply by the square root of 2 on top. Were some of you thinking I should square it? Like, you were thinking I should square it. Let's talk about why we can't square it. Because if I squared it, like I'd have 5 over square root of 2, and I would square it, and I would get 25 over 2, right? Because I'd square a square root and go away. 25 over 2 does not equal 5 over square root of 2. Like, think about an easier one. Like, if I have 1/2, and I square it, I get 1/4. That does not equal 1/2, right? We don't want to change the value of this. We just want to rewrite it in a different form. So, is it okay to multiply something by square root of 2 over square root of 2? Does that change our value? It's not going to, because what is square root of 2 over square root of 2? What does it equal? just equals 1. Because 3 over 3 is 1, 7 over 7 is 1, 2.53 over 2.53 is 1, and square root of 2 over square root of 2 is 1. So what you're doing whenever you're doing this is you're multiplying by 1, which does not change the value of a number. So you get the same value whenever you do this. Or if you type in the decimal, you'll get this. Type in the calculator, you'll get the same decimal for both expressions. But it's going to get the square root out of the bottom, because in the top, we are just going to have 5 square root of 2. In the bottom, there's a couple different ways of thinking about this. You're doing square root of 2 times square root of 2, which is the square root of 2 squared. Square roots and squares undo each other, so you just get 2. Another way of thinking about it is you're doing square root of 2 times 2, which is the square root of 4, which also just equals 2, right? If you multiply a square root by another, like by itself, you're just going to get the number underneath the square root, and the square root will be gone. So this is rationalized. So like I said, that feels a little more complicated than what you started with, but we have to do it. Example 6 is a little bit tougher. First of all, square root of 12 will break down. So whenever we're doing these, we want to break our square roots down into like simplest form before we try to rationalize. You could do it either way. It's just going to be a little quicker if you get your square roots to simplest form before you rationalize. So square root of 12, what could I break 12 into that would help me simplify this a little bit? 2 and 6 will work, but can I take the square root of 2? All right, yeah, that's it. I can't take the square root of 2 or 6, right? So while it will be equivalent, I won't be able to break it down. But Enrique tells me to do 4 and 3. And I can take the square root of 4, which is 2, but I cannot take the square root of 3, so I just leave it. So what I've got here is 3 over 4 times 2 square root of 3. And I could put that 4 and 2 together, so I could have 3 over 8 square root of 3. And so whenever you're rationalizing the denominator, you don't have to multiply by the whole denominator. You just have to multiply by the part that is the square root. So I'm going to multiply by square root of 3 over square root of 3, which will give me 3 square root of 3 over 8 times 3. And normally I'd multiply those together, but I've got this 3 right here on top that can cancel with this 3 right here on bottom. It's a 3 on the outside of the square root that cancels, not the one on the inside. And I get square root of 3 over 8. Now that one does look a little more simple than what I started with on this one. So as just a standard for this class, we don't want to leave square roots in our answers if they're in the denominator. They need to be rationalized so that they get put in the numerator for that. So, and that's going to come into play a little bit on the unit circle. Okay, questions here? All right. So, let's do this first. So, on the unit circle, all of our angles are going to be in standard position. An angle is in standard position when its vertex is at the origin. So right here is the vertex of your angle. And one of its rays lies on the positive x-axis. And I didn't put it on here, but that ray right there is called your initial ray. So for an angle to be in standard form, the origin has to be its vertex, and one side of that angle has to lie on that positive side of the x-axis. And then the other ray is called the terminal ray. And that terminal ray could be anywhere in your coordinate plane, and then you'll have an angle going from your initial ray to where your terminal ray is at. So in this case, it looks like this one's like 135, 140, something like that. Maybe 150. There, definitely an obtuse angle. For that, you can't have angles that are bigger than 180 degrees because you just go past 180 degrees. You can have angles bigger than 360. That just means you need to spin around a couple times before you land where you're at, right? So we do care about direction for these angles. So the positive angles are in the counterclockwise direction. And negative angles are in the clockwise direction. We are living in a more and more digital world where I have more and more kids tell me that they can't tell time on that clock right there. So if it's you, don't admit it and go watch a YouTube video on how to tell time. And then recognize that that second hand on that clock is going this way. That's clockwise. So counterclockwise is the opposite of that. So counterclockwise goes in this direction. Clockwise goes in this direction on the unit circle. Okay, everybody good there? All right. So before we do this slide, we are going to get our unit circle. So everybody get your unit circle that you know and love. It's everybody's favorite. I'm not going to get a bunch of math tattoos, but if I did, the first thing I would get would be a unit circle. There. So, the first thing we need to know are the angles on the inside. And this is usually, actually, whenever I give the unit circle quiz, this is usually what kids have more trouble with than really the angle, the coordinates on the outside. Usually, if they're going to miss some of it, it's usually the stuff on the inside of the circle that they miss. So the first thing I want you to notice or see here is this. Actually, no, I don't need to do that. Yeah, hold on. We're doing angles. Don't let me get ahead of myself. Okay. So right here is the terminal ray at this point. This right here, it doesn't matter whether you're using degrees or radians. 0 degrees or 0 radians goes right here on that positive x-axis. So at that point, you've got 0 degrees. You will see when we spin all the way around, we'll end up back at the same spot. So we could also call that 360 degrees as well, which we'll get to here in a second. So I'm going to do radians first because I think they are the most difficult to think about. So there are tons of tricks for learning the unit circle out there, and you are welcome to use whatever you would like. I like to teach it in like a mathematical, logical kind of way. Not just there's something at 7-Eleven or there's a hand trick where you put your fingers down or there's like those are fine, and if you need them, they're fine, but they're just tricks, right? So let's think about logically what's happening here. So we learned yesterday about radians, and half of the circle, how many radians was half of the circle? That was pi radians, right? So right over here we got pi radians. Okay, so for this, I want us to focus only on these lines that I'm about to highlight. If you have a highlighter or a different color, you might want to do this as well to help you track. I want to look at these here. So you notice I've highlighted almost everything, right? I did not highlight these little pieces right here. So we're going to ignore them for right now. Because if I only look at those yellow lines that I've highlighted, right, all of the pieces of that circle are the same size. If I only look at those yellow pieces. I told second period, if we think of this as a pie, these yellow pieces are your like normal size pieces that a normal person would cut. These little pieces are not the same size. This is the way my Aunt LaDonna cuts the pie, because she is always on a health kick. So if she's cutting it for you, you're getting a tiny sliver. We'll talk about Nanny Betty size pieces later. If Nanny Betty's cutting the pie, you're getting like half of the thing there. But these are just normal size pieces, right? And we know that half of the circle equals pi. So in that top half of the circle, we could think bottom half as well, but let's just think top half. Top half of the circle, how many pieces of pie do I have? In that top half of the circle. I got 1, 2, 3, 4, 5, 6, right? So there are 6 pieces in the top of that circle. So this first angle right here is pi. So I need to always make it look messy. I'm going to put my radians on the outside. It's pi divided by 6. All right, so the size of one of those slices is pi over 6. So if you have a pencil, you are welcome to, or an erasable pen, you are welcome to do what I'm about to do with me. If you only have a pen, I'd hold off because I'm going to change some of the things that I write down. So if you remember a unit circle, like you got a lot of crazy like radians, right? But here's what's happening. If this is pi over 6, then this is 2 pi over 6. And if you got a pencil, feel free to write that down. If you only have a pen, you might want to hold off because we're going to erase it here in a second. So this is pi over 6, this is 2 pi over 6, this is 3 pi over 6, this is 4 pi over 6, this is 5 pi over 6. I've already got pi right here, but I'm going to write down 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. And if we want to, we can put 12 pi over 6 right here, but we do already have 0 radians at that point. So 12 pi over 6 and 0 radians are the same position. So do you remember it being as easy as just counting around like that for the unit circle? Like, is that what you wrote down? There, you can't leave it like this. 2 pi over 6 was not anywhere on that unit circle. But the reason it's not is because 2 pi over 6 will reduce. What does 2 over 6 reduce to? 1 over 3. So 2 pi over 6 reduces to pi over 3. So that's the value on the unit circle that you probably had to memorize. And you may have already seen someone do this where you're like, come on, Ms. Hyatt, I already knew that. But if you haven't, I think it's really helpful to realize what's going on there. And then 3 pi over 6, that reduces. 3 over 6 is 1/2. So this is pi over 2. And if you have a pen, you can join me now in fixing all these. 4 pi over 6 reduces. 4 over 6 is 2 over 3, so we get 2 pi over 3. 5 pi over 6 will not reduce, so we leave it. 6 pi over 6 reduces just to pi, which we did already have written there. So I'm going to just erase that one. 7 pi over 6 does not reduce. 8 pi over 6 is going to reduce to 4 pi over 3. Um, 9 pi over 6 is going to reduce to 3 pi over 2. 10 pi over 6, there went my highlight. 10 pi over 6 reduces to 5 pi over 3. And then 11 pi over 6 does not reduce. 12 pi over 6 reduces to 12 pi over 6 reduces to 2 pi. Again, you can put either one of those on that line. You don't have to have them both. You can put them both if you want, but 0 and 2 pi are the same location. Now, I did radians first because they're harder to wrap your head around. What a lot of times I see is kids don't realize that you're counting up by pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, because it doesn't feel like that when you see pi over 6, pi over 3, pi over 2. Those don't feel like the same increments because they've been reduced, but they are for that. So degrees is even easier. I am going to have you memorize degrees, although we don't need them for our exam. There's just like a lot of places in, like if you go take physics or something, like where you might need it. So we're gonna memorize those as well. Plus, kids don't have trouble with degrees; they're easier than radians anyway. So this would be 30 degrees right here. So all you have to do for your degrees is count around by 30. So 30, 60, 90, 120. 150, 180, 210, 240, 270, 300, 330. Okay. And if you want to go back here, 360. So if you can remember just that, you've got most of the inside of the unit circle filled in. We're going to do something similar now, but in this case, we're going to use, we still have these lines we need to find, right? These right here need to be found. Right here, those 4 we have not found. I'm going to highlight these green and these green as well, because if I do that, it's a little hard to do because it gets a little busy with the colors going on. But now we want to ignore the yellow lines, pretend they're not there, and only think of the green lines. So if we only had the green lines, top half of the circle, how many pieces is it cut into? If you're just looking at green lines. 4. 1, 2, 3, 4. So that first green line is going to be pi divided by 4. So if we think about just those green lines, this is like the piece of pie that my Nanny Betty would have cut you whenever she was alive, like getting a big chunk right here. So if we're looking at these bigger pieces, these pi over 4 pieces, I can do the same thing and count around. So this is pi over 2. This next one would be 2 pi. I'm sorry, pi over 4. This would be 2 pi over 4. But 2 pi over 4 reduces to pi over 2, which is what we've already got there, right? So we got 2 pi over 4. This is 3 pi over 4. This one is 4 pi over 4, which reduces to pi. Then we've got 5 pi over 4 right here. 6 pi over 4, which reduces to 3 pi over 2. And 7 pi over 4. And then if we want to go around, we got 8 pi over 4, which is 2 pi. That gets all of our radians. And we want to do the same with our degrees. So that first one would be 45 degrees. 45, 90, 135. 180, 225, 270, 315. And so that gets all of our angles and our radians on the inside. Double check to make sure you've got everything right. You might even want to trade with your neighbor and get them to check it, because if you memorize it incorrectly, obviously that will be a problem for you. Double check mine, make sure I didn't mess up. Okay. Questions? Doing good here? Got the insides all worked out. Also, you are one quick Google away from 1,000 unit circles that you can check us with if you are afraid that you messed up. Just Google it. You got to know all of it. So you got to know the inside, you have to know the outside, and you'll have to have the x equals and y equals up here at the top too. And we're getting ready to do that. So here's all of our inside. Right, we've got all of it. So those are our angles. Let's look at coming up with those coordinates on the outside. So first of all, the first thing I want you to do doesn't even have to do with this first part of the slide. The unit circle is a circle with a radius of 1. That should be a 1 right there. It doesn't let me erase and it's acting crazy today. 1. That has its center at the origin. So what a lot of times I think students don't recognize is that this is a circle that's being graphed on the coordinate plane, like on the XY coordinate plane where we would graph the point 2, 7. All right, so we're talking about points on a coordinate plane. So let's see whose Math 3 skills are extra good. We can write the equation of the unit circle, a circle with a center at the origin and a radius of 1. Does anybody know what the equation of the unit circle is? Does anybody besides James know first? And then we'll see, because James obviously has everything like locked in the vault right here and can recall it immediately. Or he had a really, maybe, he probably had better teachers than the rest of us down here. Don't know. He claims not, though, on that, so. So, anybody else remember the equation of a circle?
Can we get a clue?
It ends with radius squared. Like it equals radius squared. The equation of a circle that would have a radius of 1 and a center at the origin. Okay, James, what is it? Yes. X squared plus y squared equals, I'm going to write this down so that you guys remember, it equals your radius squared, which in this particular case is x squared plus y squared equals 1. So that's a Math 3. And then you can shift that up, down, left, right by putting parentheses around that x, and you can change the center, but we don't need that for here. So whenever you're looking at this, we got the point, we got x squared plus y squared equals 1. So when we're looking at that circle, that big circle on our paper, it really fits on that coordinate plane right there at the origin, like we're actually graphing this, right? So we've got this unit circle here. So there are 4 points on that unit circle that should be really easy to find just because we know this is graphed on the coordinate plane. Okay? And those 4 points are here, 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 and here. It is your 90 degrees, 180 degrees, 270 degrees, and 360 or 0 for that. Right? Because this point right here is just the point 1, 0. Right? Then we got here, you go over left or right 0 and up 1. This you go left 1, up 0. Here you go over 0, down 1 for that. So those are those coordinates. So let's fill those in on the unit circle. We got 1, 0 right here. We've got the point 0, 1 right here. Here we've got negative 1, 0, and down here we got the point 0, negative 1. So that's the case for all of these coordinates on the outside. They are points that are graphed there. So, like if I want to take a guess at this, like 30 degrees is about right here. What do you guys, like, maybe it's about 0.86, 0.5034, like it's around there, right? Like you're graphing actual points. But, of course, like a guess is not close enough. We need to know exactly what it is. So, this is where our triangles that we were doing earlier are going to come in. So, if I have this angle right here drawn in, and that angle intersects this circle right here, for right now, I'm just going to say that that point has coordinates x and y. Okay, and then I'm going to make me a right triangle right here just by dropping that perpendicular line down to the x-axis. So that would make this a right triangle. And so if this is the point x, y, then I could label this bottom side right here x. Because that's how far I've got to go over from the origin to get to a coordinate that has an x coordinate of x, right? So like if that was 2, it's definitely not 2, but if it was 2, I'd have to go over 2, and that bottom side of my triangle would be 2, right? And so what could I label this vertical side of the triangle? That one's going to be my y. All right, so I've got those points labeled. Now, to do some trig, I need to know one side of the triangle. And the only one I got left is the only one I've got left is the hypotenuse. What is the length of that hypotenuse? Okay, it is 1. How do we know it's 1, James? It's a radius, right? It goes from the center to the outside of the circle. So it is the radius of the circle, and for the unit circle, it's called the unit circle because its radius is 1 unit, right? So on that unit circle, all of those lines going out, all those yellow and green lines that I've got highlighted there from the center out to the edge, they have a length of 1 for that. So now, using what we just learned or remembered about special right triangles, I've got the hypotenuse. Special right triangles in a 30, 60, 90, I want the short leg first. Short leg is easiest. So if I try to find the short leg, which is my y, what do I need to do? On that 30, 60, 90, let me draw it the same like orientation as we had here. 30 degrees. That short leg is the side that you want to know. To find the hypotenuse, you multiply by 2. To find the long leg, you multiply by the square root of 3. But we don't have the short leg. We've got the hypotenuse. So if we want to go backwards to the short leg, what should we do? Divide by 2, right? So if we do 1 divided by 2, y is going to equal 1/2. So this y coordinate right here is 1/2. In this case, the shorter side is this side over here. So the other triangle that we were looking at was like turned differently. We'll see on the 60-degree angle, it'll look more like the one that we had on the earlier example, but it's turned differently. So it's whichever one is the shorter of the legs is what you're going to get whenever you divide. There. And so now that I have that this side right here is 1/2, what do I need to do to find the x? I could use regular trig, but if I'm trying to use special right triangle rules.
Are you going to make us do special right triangle rules on the test?
You have to have the unit circle memorized. We're just developing it right now. It is useful for unit circle because the calculator is going to give you decimals. It will not give you an exact answer for that. So, in unit circle, you have to have exact numbers memorized for that. So, for this, if I know the short side, right? Short side is this side right here. I need to multiply by the square root of 3 to get that longer side. So short side is 1/2. So 1/2 times the square root of 3 is going to give me my x value, which we can put that together by making the square root of 3 over 1, which gives me square root of 3 over 2. And depending on how well you know your unit circle, that's your x and y coordinate for that first point at 30 degrees.
So if we just do that, we can
This is where it comes from. It's coming from trig. So, like, you could also set up trig. We're not going to have to do it again if that's what you're asking. Like, now that we know it, we don't have to go back and do it again. But this, if you think of that unit circle right there, where we're at, on that unit circle, what we're looking at is, like, for this first point in that picture, that triangle we just looked at is right here, right? So these coordinates right here are square root of 3 over 2 and 1/2. So, like, I'm not going to make you reproduce that, where you've got to remember those special right triangle rules and do that. You need to have this memorized. They're just helping us come up with where we get that. I could have also done it with setting up trig, where we could have said, like, sine of 30 degrees equals y over 1, and we could have, like, found it. But if we do that, the calculator does not give us exact value, so it wouldn't give us square root of 3 over 2. So that's why I went with this way. Now, this also helps me because you are graphing points right here. So if you look at that triangle, you got to go over a bunch and up a little bit, right? If we want to, like, really generalize this here. You go over to the right more than you go up to get to that point. Which one is bigger, square root of 3 over 2 or 1/2? Square root of 3 is bigger than 1, right? Because square root of 3, like, square root of 1 would be 1, right? So square root of 3 over 2 is bigger than 1/2. So the square root of 3 comes first. That's your x coordinate. You go further over to the x direction and then up, not as far, right, to 1/2. If you think about it, like, I'm going to graph this over here. Let's graph this on our unit circle. When I graph square root of 3 divided by 2 and 1/2, notice it puts decimals right here. It's 0.866, roughly, that's rounded a little bit there, and 0.5. So if you look at that coordinate, it is halfway between 0 and 1 on that y-axis. Your y-coordinate is 1/2. Over here, between 0 and 1, you're a lot closer to the 1. That'd be about 0.866, right? So think about, like, actually graphing that point. That helps me remember which comes first, square root of 3 over 2 or 1/2, because that's another thing students get mixed up a lot. All right, I know it feels like this is going to take so much longer, but we're going to move pretty fast from this point. Okay, questions here? All right, we got us 1 point. All right, now let's do a 45, 45, 90. They're a little easier. So in a 45, 45, 90 triangle right here, I'm going to call this x and y again. And so in that right triangle, that bottom side would be x, the top side, or the vertical side would be y. What's that radius right there? It would be 1. So in a 45, 45, 90 triangle, if you know the legs, you can multiply them by the square root of 2 to get your hypotenuse. In this case, we know the hypotenuse. So what should we do to find the leg? Divide. And does it matter whether it's x or y in this case? They're going to be equal to each other, right? So x or y is going to equal 1 divided by the square root of 2. And here's why I made you rationalize, because they're not going to let us leave it like that. They're not going to let us leave it 1 over the square root of 2, although it is the correct value. So you're going to have to multiply by square root of 2 over square root of 2 to rationalize that, which gives you square root of 2 over 2. And because that is an isosceles triangle, both of the coordinates are square root of 2 over 2 for that point there. So that goes for our 45 degree angle. So if we flip over to our unit circle, right here at pi over 4, or 45 degrees, we want to put square root of 2 over 2. Okay, questions? All right. Last little bit here. I've got this triangle right here at 60 degrees right now. We'll call the coordinates of that point x and y. So horizontal side is always x because that's how far you go over to the right. And then y right here, that's how far you go up. What is the radius of that circle right there? 1 still, right? Now, this is a 30, 60, 90 triangle. In the 30, 60, 90 triangle, the first thing I want to find is the shorter leg, which in this case is x instead of y, right? So this is just like the triangle we did for 30 degrees, but it's turned in a different way, right? So the short leg this time is x, because if this is 60 degrees, then this one up here is 30 degrees. So x is the short leg. This time x is going to equal 1/2. And to get y, we would multiply by the square root of 3, and y is going to be square root of 3 over 2. So the coordinates here are 1/2 square root of 3 over 2. So we're going to put that on our unit circle as well. 1/2 square root of 3 over 2. Okay, questions here? All right, you got this first quadrant. You're basically good to go from here, because the last part is pretty simple to fill in, because all you got to think about are the signs of the quadrant. So this is called the first quadrant. Signs for the first quadrant are both positive. For the second quadrant, which coordinate is negative, the x or the y? It is the first coordinate is the x coordinate is negative there. So we got negative and then positive. In the third quadrant, what have we got? Negative, negative, and the fourth quadrant, we've got positive, negative. So all we really have to do here is think about flipping these points around. So like, for example, if I take this 30-degree point right here, I have got positive square root of 3 over 2 is how far I go over to the right, and 1/2 is how high up I go. If I want to do this coordinate over here in the second quadrant, I need to go to the left that same amount, right? So instead of having positive square root of 3 for my x coordinate, I'm going to have negative square root of 3 over 2. Sorry, I didn't say over 2 part. And then I go up 1/2. So for that point, my x coordinate changes signs, but my y coordinate stays the same. And then the same thing is going to happen for the other two coordinates there. So you're going to have negative square root of 2 over 2 and positive square root of 2 over 2. And then you'll have negative 1/2 square root of 3 over 2. If we take the point that we just had and we flip it over the x-axis here to get our coordinate at 7 pi over 6, the x-coordinate here stays the same, negative square root of 3 over 2. But this time the y-coordinate is also going to be negative. So I got negative square root of 3 over 2 and negative 1/2. And then the other coordinates do the same. So I got negative square root of 2 over 2 and negative square root of 2 over 2. And then right here, I've got negative 1/2, negative square root of 3 over 2. And then the last quadrant right here, if I think about this point getting flipped down here to my 11 pi over 6, The x-coordinate stays the same. I've got positive square root of 3 over 2. The y-coordinate is going to be negative. Same thing happens with the others. I get positive square root of 2 over 2 and negative square root of 2 over 2. And positive 1/2 negative square root of 3 over 2. We do still need to fill in the two lines up there where it says x equals and y equals, but this is basically the like what you need to memorize for the unit circle. So you need to have that. Now, you'll have time. I'll give you a blank paper just like it looked whenever I handed it out. You've got some time where you can kind of reason through it instead of just having to have it all just immediately producible. So you can work on it. Now, I might eventually have to call time if you're just sitting there forever, but you should probably be able to do this in about 5 minutes, definitely under 10. Okay, questions, although it's taken us an hour. We did do some review first, but I want to make sure everybody understands it pretty well. Questions here? Okay, we got just a little bit more that we need to do with this, and I just hit the wrong thing. Now, let's talk about what in the world this has to do with sine and cosine, because so far we've just found like coordinates on a circle, right? But here is where this starts to line up, okay? So I'm just going to use the point 30 degrees, but this would be the case for any point on the circle, even the points that are not unit circle points. This would still apply to as well, any point that's on this circle. So again, I'm going to do the same thing I just did. I'm going to call this point x and y, although we do know what those values are now. And so this side is x and this side is y. Right. So this would be the case for any problem. If I want to find sine or cosine of an angle, right? Sine of an angle, particularly 30 degrees, but it could be any angle, right, would equal, sine is opposite over hypotenuse, right? So the opposite side would be the y in this case. What is the hypotenuse for that triangle? It is 1, because this is a 1 unit circle right here. So sine of 30 degrees just equals the y coordinate of that point, which we just filled in. So the coordinates of this point were square root of 3 over 2 and 1/2. So sine of 30 degrees would be 1/2. That would be our value. Now you have, a calculator all the time. You've never, unless you leave your cell phone at home on accident, you have a calculator that will do trig all the time. This was huge, 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 huge before calculators as far as just calculating things. For us, it's not as important anymore because we have calculators available, but it is still the link between the triangles and the sine graph that we will look at on Monday. For that, cosine of 30 degrees, that would be adjacent over hypotenuse. And so the adjacent side here is x over 1. So my cosine of 30 degrees is going to be the x coordinate of that point. So cosine of 30 degrees is square root of 3 over 2. So on our unit circle here at the very top, it says x equals and y equals. X equals, we're going to put cosine of theta, and y equals sine of theta. So what this means is if I need to know sine of 30 degrees, I'm just going to look at the y-coordinate at the 30-degree spot, which is 1/2. If I need to know cosine of 135, I just go to the x-coordinate at 135, which is negative root 2 over 2, right? So you can use this to find trig values. So that's one of the things that we're expected to do with this. So, for this, I did not put a really important piece of information here. I should have included this one important piece of information before we see if we can do this. I should have said that tangent of theta equals sine of theta divided by cosine of theta. Have you guys, I don't know if we do that in Math 3. You guys did do it in Math 3, maybe? Think so? I can't remember. I think we do. But tangent is always sine over cosine. So if you see a tangent like we see in a couple places, then you need to take your sine value, which is your y-coordinate, right? We could say y-coordinate divided by your cosine value, which is your x-coordinate. And you might have to do a little work on those. The rest of these are going to be ones that you can just like spit out. So, I'm going to split screen this with my unit circle here so we can be looking at it. So when I am asked to find sine of 3 pi over 2, I'm going to look at my unit circle. I'm going to find 3 pi over 2. It is right here. And then sine is my y-coordinate. So sine of 3 pi over 2 is going to be that y-coordinate right there. I will get negative 1. Now, I gave you a couple on here that have negative angles. Okay, so they're a little bit trickier. If I have negative pi over 6, that means that instead of going up pi over 6, like counterclockwise direction pi over 6, I need to go clockwise direction pi over 6. So we could say tangent of negative pi over 6 is the same as tangent of what other angle right there? What would we call this point right here? We could call it negative pi over 6, but it's in the same spot as 11 pi over 6, right? The value that's actually on the unit circle. So tangent, I realize I don't have room to do this. Tangent is sine, which is negative 1/2. Make this over cosine, which is square root of 3 over 2. Let me make this larger again. Okay, so they're probably not going to let us leave the answer like that, but dividing fractions is easy as pie. So I'm going to flip the second and multiply. These 2's right here can cancel. I get negative 1 over root 3. It also won't let us leave it like that because you got a square root in the denominator. So you would multiply by square root of 3 on top and bottom. And we get negative square root of 3 over 3. That goes with 9, not 12. I ran out of room. Okay. Try as many of these as you can right now. Some of them are really quick. Like sine of pi should be super quick. The tangent's a little harder. Negative angles are a little bit harder. We might not get to it today because we're about to run out of time, and we'll do a couple others first, and we'll practice it more on Monday. What did you guys get for sine of pi? Sine of pi, 0. Do you guys agree? right? Because on that unit circle right there, pi is right here. Y coordinate is your sign. Very good. Negative 3 pi over 2. On that unit circle, it's the same distance as going around the pi 3 pi over 2, but you've got to go the opposite direction. So here, you got pi over 2, 2 pi over 2, 3 pi over 2. It is the same as cosine of positive pi over 2. So cosine, which coordinate is that, x or y? X. So you get 0 for that one as well. 5 pi over 4, it is on the unit circle. 5 pi over 4 is on the unit circle right here. Okay? Tangent, when you do sine over cosine, so y over x, which is going to be negative square root of 2 over 2 over negative square root of 2 over 2. What is that going to equal? Like, I could do dividing fractions easy as pi, flip second, multiply, but that is just something over itself, which equals 1 for that. So you just get 1 for that one. And we are about out of time, so I am going to stop for today. We are going to practice more. Second period did not get as far as you guys because we had to